Hi, it's Mr. O'Rourke again, and in this video we're going to talk about chemical bonding a little bit, ionic and covalent chemical bonds. In the last video I showed how electrons were arranged in the atoms and how you can predict that arrangement from the periodic table. In this video I'm going to go over how the elements chemically bond together. All atoms want to be stable. That stability comes from having a full valence shell of electrons, their outermost shell needs to be filled. In the first level you only need 2. In the rest it wants to have 8. 8 is kind of the magic number for it to be stable. So they're most stable when their valence shell is full. If they do not have 8 electrons in their valence shell, then they're unstable. Elements will bond chemically because they're trying to achieve that stability by either stealing an electron, giving an electron away, or sharing an electron with another atom in order to get that full valence shell. Now, the first energy level or shell can only hold 2 electrons. Okay, all the other shells are most stable when they have 8. So let's take a look at this. When I look here, we'll talk about ionic bonding. That's the easiest one to talk about first. So when we talk about the periodic table and things, we're going to look at a couple elements. Now, if I look at sodium and chlorine, when I look at those and I can look at the periodic table, sodium has 1 electron in its outermost ring. So that's the only one I care about. Chemical bonding only deals with the valence electrons, the outermost electrons. The inner electrons, don't worry about them so much. Sodium and chlorine over here, element number 17, has 7 electrons in its outermost shell. So when I look in here, I will just draw the valence electrons, the ones that are on the outside. Sodium has 1, chlorine has 7. Sodium wants to get rid of that 1, and chlorine would like to take it. Now, when I look at the electron diagram, and I look at sodium here, it has its 1 electron, and now it wants to have 8. It can try to attract 7 more electrons, which is unlikely. Okay, it's only 11 protons. Okay, it already has 11 electrons. To attract 11 more electrons is very unlikely. But if it gets rid of this electron, well, look what it has. It has 8 in its outermost shell if it loses that electron, and it's stable. That's what sodium would like to do. On the other hand, chlorine over here, okay, has 7. It needs 1 more to complete it. To get rid of these 7 is very unlikely. It's more likely it can trap another electron or get another electron to go there. So, with that in mind, we're going to look here. This sodium gives that electron away. It's stable. Chlorine gets the electron. It's stable. So that's basically what happens. Okay, the sodium and the chlorine come together. Now, once that happened, in a couple videos before this, I talked about ions. Okay, the sodium has 3 protons, which are 3 plus charges. Okay. If it loses an electron, it had 3, now it has 2 electrons, so you would have 2 negative. So when you go through and look at that, 3 minus 2 equals 1. So you would have a charge of 1 plus. So you would have a positive charge on this sodium over here. Okay? The chlorine, on the other hand, okay, has 17 protons. Okay? 17 protons. So that's 17 positive charges in that. The chlorine now has 18 electrons. So you have 18 negative charges. 17 minus 18 equals a negative 1 charge. Chlorine becomes negatively charged. Positive and negative, opposite charges attract, just like a magnet. This is how it chemically bonds. These opposite charges pull them together. Now it's a different substance. It's not sodium anymore, and it's not chlorine anymore. It's sodium chloride. Okay? Sodium metal by itself it will kill you if you eat sodium metal by itself. Chlorine gas, if you breathe just chlorine gas in, that will kill you as well. Sodium chloride together in a compound, you need that to survive in your body. It's a totally different substance. Chemically, it's very different. Makes your pretzels taste good. Okay? So this is the difference. This chemical bonding changes two other things into something completely different. Okay, this is a chemical reaction that we have here. So this bond, this is a totally new substance here called sodium chloride. Now, this will happen through any metal and nonmetal will bond ionically. Any metal and nonmetal on the periodic table. So I can look at any of the nonmetals over here, okay, which I can separate them. The metals are anything to the left of this. The nonmetals are to the right, but here is the breakoff. These are the noble gases. They don't chemically bond with anybody. All these guys here. They already have 8. They have no reason to take an electron or give an electron away, so they're inert. They don't bond with anybody. All these guys are trying to gain electrons. All these guys are trying to lose electrons, so they get together ionically in that way. So when I look at this, the sodium chloride, I can look at calcium and sulfur. Calcium being in the second, come on here, there it goes. Calcium being in the second has 2, sulfur has 6. Sulfur needs 2. Calcium needs to get rid of those 2, so it'll have the full 8 behind it. So when we look at the bond, these 2 electrons are going to fill in here, 2, 4, 6, 8. So when I look over here, we get that. Now, because it has lost 2 electrons, if it lost 2 electrons, it's going to have a +2 charge on it now for the calcium. The sulfur, because it gained 2 electrons, has 2 extra minus charges on it. This will be a -2 charge on the sulfur. Opposites attract. Boom, they're put together. That's an ionic bond. 2 ions, calcium lost electrons, it's an ion. Sulfur gained electrons, it's an ion. Ionic bonding. And this is how chemical bonding works between metals and nonmetals. Okay? Now, the final one that I want to talk about is covalent bonding. Covalent bonding only happens between nonmetals. Metals aren't involved in this at all. Okay, there's no stealing or giving away of electrons in covalent bonding. When we look at the elements that are nonmetals over on this part of the periodic table, they need to get electrons. Okay, now they're not strong enough to steal them from the other guys, so they're going to share instead. Okay, they're going to share electrons, and by sharing the electrons, they both get the benefit of having that rule of 8, having 8 electrons in their outermost shell satisfied for stability. So let's take a look at how some of this covalent bonding works. We look at 2 elements, hydrogen. Okay, these are both nonmetals. Okay, even though hydrogen is in the first group, that's the one, like I said, the first energy level, the hydrogen and helium act a little differently. They're a little bit different. So, neither of them is strong enough to steal the electron from the other one, so they're going to share them. Okay? What we do when we talk about a covalent bond, we just draw a bar between them. Now, they want 2 electrons when you're hydrogen, because you have the first energy level can only hold 2. Both of them want 2. These 2 electrons are going to go around both of these atoms. Okay? They kind of go around in a crazy, swirly way. But because both electrons go around this hydrogen and both go around this hydrogen, they can feel like they have their full valence shell. Okay, so that's hydrogen. Fluorine works in the same way. They both have 7. They're going to hook up and share 1 electron each. Okay? Come in here with a bond. Now, when I draw this covalent bond as a bar, that means these 2 electrons count for both of these atoms because they're going around both of the atoms. Whatever crazy way. 2, 4, 6, 8. Good for this guy. 2, 4, 6, 8. Good for that guy. So they're happy and content. When we look at oxygen, oxygen is the air we breathe. Oxygen has 6 electrons in its outer shell. It wants 8. Both of them want 8, so they'll share 2 each. That's what makes oxygen gas. So you bring them close, they come together, they both share 2 pairs of electrons, and that's how you get your oxygen. And it can go on and on for different things. And because of the sharing, you can come up with lots and lots of different patterns. Okay, this is what makes organic molecules so malleable, to come up with so many different shapes, because so many different things can be put onto them. With ionic bonding, you got metal, non-metal, and that's it. Okay, you can't really make as large a molecule, but with this, you can. If I want to make carbon dioxide, the carbon, which is an interesting guy, being in the periodic table, has 4 electrons. It won't give those 4 electrons up easily, but it's too weak to attract 4 electrons to it. It will only bond covalently. Okay, so when we look at what's going on here with oxygen, this oxygen needs 2, so it's willing to share 2 oxygens, just like it did with that other oxygen molecule. They just shared 2 each. We'll share 2 electrons with this carbon. Well, this carbon still has 2 other electrons it needs to pair, so another oxygen can take those up, and you will end up with, once they get close together, they'll pair up. You get CO2. You have the 4 electrons around the oxygen, and the 2 electrons that were unpaired that they needed to bind up with. Take 2 from carbon, 2, 4, 6, 8, carbon 2, 4, 6, 8, oxygen 2, 4, 6, 8, carbon dioxide. So this is how, excuse me, this is how covalent bonding works. By sharing, they achieve their stability. They achieve what that 8 electrons in its outermost shell. By giving away electrons or sharing, they get that stability. Now, when they do that, they become compounds. Okay? Elements are the single ones. Anything you can see on the periodic table is an element. And once you have 2 elements that react chemically and form one of those bonds, you have a different substance, just like the salt. Okay? Oxygen gas is different than just plain oxygen. You can look at the carbon dioxide. It's different than just carbon and oxygen. So, when we go through, we're going to talk about, in my next video, we're going to talk about mixtures, substances, compounds, elements. We're going to define those and find out how can we tell the difference apart between them. This is the foundation that will allow you to understand that. Most students struggle with compounds and mixtures. They don't really see what's the difference between them. Hopefully this will put them on the right path. This is also stuff that they're going to need next year. Hopefully this will help them get on the right path and be ready for next year. And they're going to tear it up. Thanks again.